Welcome to Oregon Building Codes Division's Residential Energy Code Training video for new home construction. This video is part 1 of a 3-part series on energy-related topics for Chapter 11, Energy Efficiency, included in the 2023 Oregon Residential Specialty Code, the ORSC. Part 1 covers general energy concepts. This is a prerequisite for Parts 2 and 3. This presentation is intended for both new staff and existing staff looking for a refresher on Chapter 11 of the ORSC. This video is supplemental to the required code change training course. You should have taken the 2023 Chapter 11 Code Change Training course. If not, a review of the course after watching this video is suggested. The videos have time markers, so you can skip a lot of the introductory materials. Also, before watching this video, it helps to familiarize yourself with the residential technical bulletins. Whether for the structure, found under the Residential Program page, or energy provisions, found on the Residential Energy Program page, these are great resources. It's strongly encouraged to review the latest bulletins either before this course or immediately afterward. Our presenter for this training is Mark Heiser, our Mechanical and Energy Program Chief. As a reminder, our team is a technical resource for our local government partners and other customers. Division staff are available to answer questions should you have them. Feel free to email us or call us directly. We are always happy to assist and appreciate hearing from you.
So what is Chapter 11 of the ORSC? Chapter 11 sets specific energy efficiency requirements for the ORSC. Efficiency provisions for dwellings have been in Oregon's building code since the very first statewide code was put into effect in 1974. Chapter 11 residential provisions only apply to dwellings constructed under the 2023 ORSC. National model codes require multifamily structures 3 stories and fewer to be constructed to the residential model code. However, in Oregon, if the customer is constructing a multifamily building using the Oregon Structural Specialty Code, regardless of the number of floors, that building will use Chapter 13 of the Oregon Structural Specialty Code, which is also known as the Oregon Energy Efficiency Specialty Code. The OEESC uses ASHRAE Standard 90.1 as the basis for the code. So again, in Oregon, if the customer is building under the 2023 ORSC, Chapter 11 of the ORSC applies. This course will be broken into 3 parts. First, we will review the code and the background of the development of important code sections. We will review some of the concepts for energy efficiency and how these are addressed in the code. The code allows builders substantial flexibility in constructing an efficient home. Just like there are options for constructing a foundation, wall bracing, roof trusses, or roofing materials, the energy provisions have options as well. And the code requirements can then vary based on the options selected by the builder. With the background of the code covered, we'll move into the plan intake and plan review for new construction. We've all seen plans that can vary from production builder plans submitted in CAD format to hand-drawn sketches that have been put together by the homeowner. Understanding of the concepts helps you inform the customer at plan intake of items that might need to be added to the plans, as well as background on why certain items need to be shown on the plans. Good review at plan intake can make the plan review process go smoother. And there's less chance of having surprises during the inspection process. Each jurisdiction may have different procedures. The intent for plan review is to cover the basics. Finally, we'll cover the inspection process. Again, your department may have specific procedures for review in the field, whether it's your pre-cover inspection or your review of sheathing nailing patterns or of bracing or tie downs. The focus of the video is to cover the minimums and provide guidance on important items to review in the field. This training is focusing on the prescriptive requirements for new homes. We are not covering the Energy Rating Index performance path, which uses a HERS rating or equivalent. Alterations and additions are not covered. The code change training course has guidance and you should familiarize yourself with that portion of the code change video. Finally, change of use and change of occupancy are not covered in specific details here. If you have questions on these areas, feel free to reach out to division staff. Chapter 11 Introduction and Background. Before starting, just a quick reminder that all the provisions of the Oregon Residential Specialty Code fall under the authority of the Residential and Manufactured Structures Board. This board has the authority over all aspects of construction under the ORSC. The board sets minimum requirements for the structure, as well as the mechanical, electrical, and plumbing systems. The board relies on the electrical code and plumbing code as the basis for the ORSC, but can modify these codes for use within the ORSC if they wish. Chapter 11's energy provisions cover the envelope, structural areas, mechanical provisions, as well as electrical and plumbing provisions outside of the electrical and plumbing codes. So members of your team may review separate code areas on the plans, whether structural, mechanical, electrical, or plumbing. Whether reviewing plans or inspecting in the field, anyone enforcing the ORSC should be familiar with Chapter 11 and where the energy provisions may overlap with their specialty. So let's move to the code concepts for 4 focus areas of Chapter 11. There's the thermal envelope, additional measures, mechanical and plumbing systems, and lighting and power. The envelope. Before we start, the envelope is not something you put a stamp on and mail to a relative that still uses a flip phone. The envelope provides the shelter between you and the outdoor environment. It retains warmth in winter, limits heat gain in summer, including solar effects, and limits unwanted air infiltration from the outdoors, keeping air that you've heated or cooled indoors. Controlling infiltration is an overlooked area for efficiency. In homes built less than 20 years ago, a majority of the furnace sizing was to address the heating load from leaking air. Another important but often overlooked area is how the envelope addresses moisture in the air. The envelope regulates the movement of water vapor into and out of the home. Good design will avoid buildup of moisture that can lead to damage in the home. The envelope is a thermal assembly that separates the indoor conditioned space from the outdoors or from unconditioned spaces that aren't heated or cooled. Examples might be a ventilated attic, a crawl space, or an unconditioned garage. The envelope isn't just the insulation, it's the sum of the parts. The envelope may start at the floor slab if it's a slab on grade home, or under the floor if there's a crawl space. There are walls, both above grade and below grade. A ceiling or roof could include the ceiling below a vented attic, where the attic is outside of the thermal envelope. Alternatively, some construction may have an insulated roof with an unvented attic inside of the thermal envelope. The main point is that the dwelling's thermal envelope should be continuous in its separation of the conditioned space from the outdoors or an unconditioned space. When considering the envelope, when you see the term fenestration, this applies to windows, doors with glazing, and skylights. The ORC sets a minimum requirement for different assemblies within the thermal envelope. Here is an example of different thermal assemblies that make up the total thermal envelope. Note that the insulation is shown in green. A quick note that this diagram is for many different climate zones. In Oregon's climates, the code does not require insulation under a basement floor, nor is insulation required under the typical slab-on-grade floor. There are some exceptions, such as a floor with radiant heating installed in the slab, or if a customer is installing the insulation to improve the performance of the overall building thermal envelope. The diagram covers examples that might have unvented assemblies. This could be a vented rafter space, or it could be unvented, which requires some insulation above the roof decking. See ORSC section R806.5 for requirements for an unvented attic or an unvented rafter assembly. There are also specific examples of crawl spaces. This example has insulation between the floor and the crawl space, so the crawl space is outside of the thermal envelope. We'll discuss this later, but it's important to know whether an attic or crawl space is ventilated space when considering whether mechanical ductwork is to be installed inside or outside of the thermal envelope. While many homes have crawl spaces, some are built with slab on grade or with a basement. Insulation for a slab can either be at the slab edge or under the slab. BCD has developed a technical bulletin to provide guidance on how slab edge insulation can meet code. Envelope compliance. So, after reviewing the components of the envelope, we're going to dive into the methods for compliance. There's a prescriptive method where each assembly meets a minimum R value of the insulation that is installed in the assembly, or an equivalent U factor of the overall assembly, so the performance of the total assembly. The prescriptive values are found in Table N1101.1. If all of the home assemblies are constructed to the minimum table requirements, the building meets code. But if one or more assemblies can't meet the prescriptive minimum thermal performance requirements, the customer can trade off. An assembly that performs better than the prescriptive minimum can be used to offset the assembly that doesn't quite meet the minimum requirements. The trade off is a weighted result where the area and U factor for each assembly is compared against the area and U factor of the assembly that meets the code. Let's look at Table N1101.1, which lists the prescriptive minimum performance requirements for Oregon homes. First and easiest way to determine compliance is to install the prescriptive minimum insulation levels for each assembly type. These values are found in the equivalent value column of the standard base case header. One example is for walls. Install insulation meeting at least R21 between the wall studs using the intermediate framing technique, and this wall meets code. One quick note, the higher the R value, the better the performance. Or, if the customer wants to build a non typical wall type, they need to meet the performance of the assembly found under the required performance column. The U factors listed under this column are the equivalent performance of the prescriptive assembly with insulation meeting the R value under the previous column. The U factor includes the performance of the sheathing, air films, interior wallboard, etc., but adjusting the effective value of the insulation if the insulation is installed between framing. For example, walls where the R21 insulation is installed between studs does not perform equivalent to R21. Heat is also passing through the studs faster than the insulation, so the effective R value of the studs and insulation combined is less than R15 for this portion of the wall assembly. One quick note, U factor is applied per square foot of assembly, which means how much energy will pass through the wall per square foot of area. Some values are in the required performance column are not in square feet. Looking at the basement below grade walls, a C value is used. This is applied per linear foot of wall. The C value for a below grade wall, regardless of the height of the wall, is applied to the length of the basement wall. Note that the C factor for these walls can be achieved with either R21 insulation installed between wood studs or with R15 of continuous insulation, abbreviated as C.I. in codebooks. This R15 is not interrupted by studs or other framing. Another insulation type measured in linear feet is the F factor for the insulation installed at the slab edge perimeter. A slab on grade home with R10 insulation installed along the slab edge extending 24 inches below grade has an F factor of 0.52. When we consider windows, doors, and skylights, these are always labeled with a U factor. These materials have special testing standards and are labeled with U factors. This accounts for the total assembly of the fenestration, including the glazing, the frame, and other items as shipped from the factory. We'll discuss the labels that come with the windows at a later point. Table footnotes and special conditions. So, from Table N1101.1, paren 1, there are some special considerations you should be aware of. First, intermediate frame walls are described later in section N1104.5.2. Headers in the wall should be insulated. The intent is to achieve a minimum of R10 insulation in any header cavity. Corners are requiring special attention to get insulation into the corners and at wall intersections, and the framing is at 16 inches on center, like standard framing. Advanced framing is where an intermediate frame wall extends the stud spacing to 24 inches on center. A heated slab is where there's an actual heating element within the slab itself. This doesn't mean that the slab is in a heated dwelling. When it comes to the U factor of 0.27 requirement for fenestration, some windows can't meet this level. However, the weighted average of the U factors, where some are higher and some are lower than 0.27, can be used. More notes and special conditions from the envelope table. Vaulted ceilings. These ceilings don't have to perform as well as ceilings under a vented attic, which requires R49 insulation. A gross area of the vaulted ceiling space equal to one half the total conditioned floor area can use a lower U factor of 0.033. To clarify what this means, the total conditioned floor area is of the total building, not just the space under the roof. This applies to half of the ceiling area for a one-story home. But for a two-story home, it could be possible to have a 100% vaulted ceiling installed at U 0.033. Looking at the different U factors for different roof construction types, a vaulted ceiling with rafters could install R30 extending across the full extent of the cavity and comply. A vaulted ceiling with a scissor truss needs to have R30 advanced framing, unlike a rafter ceiling where the insulation depth is constant over the entire roof. A scissor truss gets extremely shallow at the outer edges. To get the equivalent of R30 across the entire roof, the advanced framing method must be used. Advanced framing for a roof requires a raised heel at the edges so that the depth of the insulation from edge to edge can be R30, just like in the rafter ceiling. If the scissor truss isn't advanced or full depth of insulation at the outer walls, then R38 standard insulation could comply. Standard installation squishes the insulation as the height of the truss reduces as you move toward the outer edges. So, what can be done if one or more thermal assemblies does not meet the prescriptive table, either the R value or the U factor? The customer can use trade-off table N1104.1.1. Under this path, the customer first calculates the performance of the home as if it were constructed using the prescriptive code U factors from table N1101.1. The U factors are multiplied times the area for each assembly. This is called the standard base case. Then the proposed alternative is calculated. This is the design condition and is a trade off of thermal performance that uses the same areas, whether the walls, roof, floors, fenestration, etc., as used in the standard base case. These areas are multiplied by the proposed alternative case U factors. Some of the U factors will be higher or worse than the prescriptive code, while other factors will be better than the prescriptive code. The result for the assemblies are then summed, and if the total for the designed proposed alternative is less than or equal to the total for the standard base case, the trade-off is acceptable. So here is the trade-off spreadsheet table. You can see the standard base case columns with the prescriptive U factors already filled in. The customer fills in the appropriate areas, multiplies by the U factors, then the sum of the results are put into the code UA. Then the proposed alternatives are input. The R values of insulation to be installed, the areas for each assembly type, and the U factors are input into the table. Then the area times the U factors are put into the last column, and the sum of the design is input into the proposed UA box. The design meets code if the proposed UA is less than or equal to the code UA. So it lets in less energy than the code building. I'd like to stop for a reminder about footnote G and the F factor and C factor. These values, again, are not square foot areas, but are linear feet of slab edge and linear feet of below grade walls in a basement. So when using the spreadsheet in table N1104.1, paren 1, where would a customer find U factors, C factors, or F factors? For common wood frame assemblies, table N1104.1, paren 2 has default values for many construction types. Let's look at a flat ceiling construction with a vented attic and R60 insulation using conventional framings. This is a ceiling that has a U factor of 0.017. The designer, if using this trade-off, would put the U.017 U value in the proposed alternative column. This table has lots of options for walls, both with and without continuous insulation. R23, usually a dense packed blown-in insulation, is becoming more commonplace. The U factor for R23 insulation in intermediate framing has a U factor of 0.055. Before moving on, there are some assemblies that aren't common in residential construction. In these circumstances, the designer or builder can go to Appendix A of ASHRAE Standard 90.1 to find more assemblies and methods to determine special assembly U factors. If not from Table N1104.1 paren 2, you should get a full calculation document from the designer as part of the record drawings. Trade-off spreadsheet. The division has created an Excel spreadsheet that performs the function of the trade-off table. From the residential energy page, the envelope trade-off calculator link has an easy-to-use spreadsheet with drop-down tables for assemblies and detailed instructions on how to use the spreadsheet. This could be a helpful tool for your customers, saving them a lot of effort. After watching the spreadsheet demonstration video, we'll proceed to the next topic, additional measures. So this video will review how to use the calculator for Chapter 11 for envelope trade-off. One of the first things to do is begin at the home page of the Building Codes Division website. Go to Code Programs, and then under Code Programs, go to Energy Efficiency, and there you will find the Residential Energy Code page link. On that page, you'll find compliance tools, and what we have now is an envelope trade-off calculator for buildings using seeking to trade off portions of the envelope. You can then open the spreadsheet. Once the spreadsheet is open, you will find that you have instructions on the very first worksheet. Here you'll have instructions on how to fill out the standard base case, and that would be information relative to the prescriptive compliance path. Then, any proposed alternatives for different wall types, you would use the Mixed Alternate Wall Types tab further down. There's also a tab for Windows U factors that can also be used, and a Skylights U factor and a Doors Overall U factor. Looking to the table itself, the client can use and input areas. Anything that's in yellow is something that the client will input, whether it's the flat ceiling area, vaulted ceiling area, vertical wall areas. When you have the vertical wall area, it's the wall areas of the entire home. You do not subtract out windows. If it's a raised floor, you'll see there's a tab for underfloor, and you can input that value. Or if it is a slab on grade home, you can enter the linear feet of slab edge, or if you have a basement, the linear feet of basement wall. Those get input into this portion of the worksheet. And then the other portion is where the client or customer comes down and selects what type of insulation, say for your ceiling. If you select the framing type, you can select between different insulation values for a typical conventional framed roof insulation. R49 is prescriptive. If they have vaulted ceilings, there are different methods of either rafter framing or scissor trusses to select from, including advanced framing methods. Then for the framed walls, you can pick the type of frame wall. R21 intermediate framing is the typical wall. We have additional inputs if they have the R21 and 7 would be having R7 exterior insulation. And you can go as far as R23 framing. Should it not be on the list, say something, we even include some SIPS panels values further down. That could be input, including looking back to R13 standard framing with the old 4-inch stud method. If you have a wall that isn't in there, we have mixed or alternate frame types, the U factor tab, where you would go to this tab and put in the actual wall values, including on every one of these, we have an example wall type showing how these things would be input. You have the square foot of area and then the U factor for those specific wall types. You may have things like insulated concrete form walls. You may have other types of mass walls or CLT walls. The customer would put in the area of the walls and the U factor for those. Coming back to the main menu once again, also there is for the underfloor R value, different things that can be done for that. Also slab or under edge, slab edge or under slab amount insulation types. You can select that as well. And if you do happen to have an ICF form wall, you can put the amount of wall in here. The window values down here for doors, skylights, and windows come from the Windows tab. And they give an example of how to do windows and the area of the windows and the U factor assemblies. And it does an average based on this example. There's 175 square feet of window, and the average U factor is 0.262 for what's above. This could also be used if people are just looking to trade off the window values. They have one or two that don't meet the 0.27 required. Here's someone who shows their different windows and gets the overall U factor. Examples are included for skylights and for doors. One thing that you'll notice in here, there's the code does allow for up to 28 square feet of exempt door. So if you have an entry door that's solid core, you can put in the square footage, and the U factor of the door, you can default to the code minimum 0.2 for that exempted door. Moving on. In this case, I've shown an example building with 1,200 square feet of flat ceiling area, input walls with a total of 2,350 square feet of wall area. If you'll notice, the windows and doors have all been brought in automatically from other pages, and also 1,200 square feet of underfloor space. We're considering this a crawl space building. I input R49 conventional framing for the roof area. There's no vaulted area space. The R21 intermediate framing is the wall type, and I have R30 underfloor. And looking at this, the base case comes out to 285.33 for the U factor times area summed up. And then the proposed alternative comes out to 284.84, which is lower than the base case UA. So the total conductance over the total area of the building is better. The proposed UA is better than the base case. So this does pass. We don't have any special wall types. For our windows, we have windows that are a mix of different U factors in different areas. It comes out to a 0.269 as the average U factor, and when that gets pulled back to the main calculator, it's pretty much equal to 0.27 average U factor. And then same for the doors, showing that we have an entry door and a garage door. The entry door is exempt, so we put in a U factor. The customer puts in 0.2 for the U factor for that door. And again, going back to the main table where the calculator comes through, all of those values from windows, skylights, and doors are brought in this portion down here of the UA factors for envelope components for either any of the fenestration, whether it's windows, skylights, or doors, adds it up automatically, and then gives you a pass or fail. It will turn red and say plus point whatever or 1 point whatever in the percent improved if they aren't making it to equivalent thermal performance. So with the general concepts of the thermal envelope covered, it's time to dive into the additional measures and table N1101.1 per N2. This is an additional level of efficiency above the normal minimum prescriptive requirements of the code. The table has 7 options to choose from, allowing the builder to select the most appropriate option for their construction. Section 1101.1 requires the selecting and installation of one additional measure from this table, unless the home uses exception number 3 from section 1105.3. These homes require 2 additional measures from this table. We'll get into this exception later, but to put it simply, 2 additional measures are required for homes installing their ductwork outside of the thermal envelope. The measures range from equipment efficiency improvements to envelope enhancements, and even a combination of equipment and envelope. But because the measures are beyond the prescriptive requirements, it's important to know what measure is selected. So this is the additional measures table. The measures can include equipment upgrades. One of the most common measures for a gas home is measure number 1, increasing the furnace efficiency to a 94 efficient gas furnace or better. There are also equipment options under measure 2 for water heaters and measure 5, which is intended to address the once common all-electric or cadet heater home. There are envelope measures numbers 3 and 4, which have simple lists of upgrades. Measure 6 doesn't rely on specific envelope enhancements, but allows for a combination of envelope upgrades. The target is to have the envelope perform 8% better or more than the prescriptive minimum code tables would require for the home. Measure 7 is a combination of better air sealing of the envelope and requires that the whole house ventilation, required under Chapter 15, be provided by a heat recovery ventilator with at least 66% efficiency and a minimum fan efficiency for that heat recovery ventilator. Any of these measures, especially the envelope measures, are above the prescriptive minimum. The changes above code minimum need to be properly documented and checked in the field. Ducts inside. This is one code revision that will have the biggest single impact on home energy use. This comes from section N1105.3, installation of ducts and air handling equipment. I want to emphasize installation and location. Section N1105.2 covers the insulation of ductwork. All ducts and air handling equipment for new homes need to be installed inside of the thermal envelope. There are exceptions for some ductwork to be installed outside of the thermal envelope. And let me emphasize this is just for the ductwork. Any furnace or air handler should be located inside the thermal envelope for a new home. Exceptions from the 2021 ORC are modified for the ducts inside. First, a limited amount of duct, up to 10 feet, can be installed outside the thermal envelope or not be deeply buried. The 2021 ORSC's exception was for a percentage of total duct length, and this was very hard to either verify or enforce in the field. A second exception is that exhaust duct and outdoor intake duct are not required to be installed inside the home or to be deeply buried. This wouldn't save any energy. Lastly, three options for ducts outside of the thermal envelope that exceed the 10-foot limit are covered in sections N1105.3.1 through N1105.3.3. Customers taking these exceptions and having more than 10 feet of ductwork outside the thermal envelope have to select two additional measures from Table N1101.1 paren 2. If you haven't reviewed it by now, I suggest reviewing the updated technical bulletin covering the buried duct topics. It will help with the next few slides. So diving into the options for deeply buried ducts, Section N1105.3.1 covers the path for deeply burying ductwork located in a vented attic. The exception requires that the ductwork, insulated to R8 like any duct outside of the envelope or in an unconditioned space, must be buried under an additional R19 of insulation between the duct and the open attic space. Markers are required to show the location of the duct. This allows for maintenance within the attic without damaging the duct. One exception within this path is that any combination of duct and attic insulation can be used so long as the total insulation between the duct and the vented attic space above is at least R27. So, for example, an R5 insulated duct could be combined with R22 insulation over the top of the duct. Using section N1105.3.1 again requires selecting two additional measures. Section 1105.3.2 is for ducts located in an unvented crawl space where the crawl space itself is outside of the thermal envelope. This implies that the crawl space has R30 insulation under the floor, which thermally separates the crawl space from the occupied space above. Ductwork in this space does not need to be deeply buried, but it must have R8 insulation. As an unvented space, the air will not be exposed to the outdoor temperature, unlike in a vented crawl space. And again, additional measures must be selected. Under section N1105.3.3, the duct is located in a vented crawl space. The easiest way to think about this application is that it's just an unvented attic flipped upside down. R8 insulated ducts must be buried with at least R19 additional insulation between the duct and the vented crawl space. And just like the vented attic, there is an exception allowing for any combination of duct and floor insulation as long as the total insulation between the duct surface and the vented space is at least R27. And of course, two additional measures must be selected. Moving forward with mechanical requirements, one new 2023 ORSC item is for the use of smart thermostats. The requirement is to have an Energy Star smart thermostat. In addition, the thermostat must be capable of either occupancy sensing or geofencing. Geofencing consents when the occupant is not at the site through signals from a phone or otherwise. The building official can also accept an approved equivalent. Technology is changing quickly and alternates should be available for consideration. The list of Energy Star thermostats that meet these requirements has increased significantly between the time the code was written and the time of this recording. One additional note is that there is no requirement to have Wi-Fi to the home. There are some exceptions for not requiring an Energy Star thermostat. Any heater of 2 kilowatts or less which would cover nearly every wall heater or baseboard heater used in a typical home. Any cooling unit with less than 18,000 BTUs per hour or 1.5 tons of indoor capacity. And finally, per a statewide alternate method, any cooling system with a variable speed compressor where the manufacturer requires their own thermostat is also exempted. Because of the control of these compressors relies on special ramping up and down of the compressor capacity, as well as defrost control when the system is a heat pump. Using an Energy Star thermostat from a different manufacturer could void warranties or damage the equipment. So this is one exception for where a Energy Star thermostat is not mandated, and it is required to be approved by the building official. Let's discuss fans and whole house ventilation systems. Section N1105.6 covers fan efficiency. All ventilation fans are required to be Energy Star fans. It's easy to verify with the Energy Star label on the fan. In addition, the 2023 ORSC has a new requirement for whole house ventilation systems that use the central furnace as the outdoor intake fan. These systems are known as central fan integrated systems. The requirement is for the furnace to deliver the ventilation air at a rate of at least 1.2 CFM per watt of fan energy. To achieve this level of efficiency, the furnace would need to be a multiple speed or variable speed fan, and there would be a necessary ventilation controller to set up intermittent operation of the furnace fan to accomplish this operation. Having covered special requirements for some ventilation systems, we'd like to address the whole house ventilation system requirements from Chapter 15. We have a technical bulletin that covers most of the many ways to achieve the ventilation system requirements. There's more than one way to get air into and out of a home. However, we want to emphasize that each system needs a fan or other system pushing air into the home and a separate exhaust fan that pulls the same amount of ventilation air out of the home. This is what is meant by a balanced ventilation system. The push and pull fans have to be interlocked so that the system can be controlled by the owner. That control, usually a wall switch, must be readily accessible to the owner and clearly labeled. Just like for plumbing, regulation of lighting systems is relatively limited in the ORSC. High efficacy lighting, such as LED, is required for all lighting fixtures in the home. The code does have an exception for up to 2 fixtures to use old technology light sources, as long as those fixtures are controlled by a dimmer or other automatic controls. The same requirements apply to exterior light fixtures. Once again, 2 fixtures could use older tech, such as metal halide, as long as the fixture has automatic controls. For outdoor fixtures, this might include motion or daylight photocell controls, or even newer home automation system controls. Moving on to plumbing systems, Chapter 11 has only a few plumbing requirements. Under additional measures, if selecting additional measure number 2, high efficiency water heaters are installed. This usually entails a heat pump water heater or a condensing gas fired tankless water heater. Prescriptive requirements are limited to installation of piping for service water heating. If the pipe is not fully within the thermal envelope, the pipe must have R3 insulation. Recirculating systems also require R3 insulation on the portions of the pipe with circulating hot water. And the first 8 feet of pipe, both into and out of a water heater, requires insulation as well. High efficiency, low flow fixture requirements are found outside of the ORSC. These are found both within state appliance standards and the Oregon Plumbing Specialty Code.
Congratulations. This completes Part 1, General Concepts Training, of the 2023 Oregon Residential Specialty Code, Chapter 11. Thank you for watching this presentation. Providing useful information to all of you is important to our team. If you have questions or comments, please contact our Energy Code program. Their contact information is available on the division's website. You can also scan this QR code to get there.